In this module, we are going to learn techniques of intertemporal optimization. Maximizing some objective function is central to economics. Various maximization methods will be used, ranging from the substitution method via the Lagrangian and optimal control to dynamic programming using the Bellman equation. Most applied economic models are designed to represent economies at particular points in time. For long run models, the point of interest is far in the future when all imperfections disappear, while the short run models focus on the immediate present. In both cases, however, only one period is captured, turning them to be static in nature. These models hardly explain how the system changes over time, and they fail to provide the sequence of equilibria between the short and long run solutions. This limitation is overcome by the intertemporal models, which analyze how the economy and its inherent variables evolve over time. These allow the models to be used to find the economy's trajectory through time. These types of models have a special significance for the policymakers who are often keenly interested in how fast the economy moves towards the long run, especially when the short and long run effects of the policy are very different. These models are also used to evaluate the effect of different policies on the rate of growth. There are a number of circumstances where it is necessary to compute the time path of the economic model, which points towards the need of building an intertemporal model. The other reason for building an intertemporal model is to incorporate intertemporal optimization by agents. If some of the agents in the model choose current variables to optimize intertemporal objective functions, even short-run results will require some form of intertemporal modeling. This is true especially for accumulation of human wealth by the households, which has implications upon future labor income. Many such current variables with a stream of effects in future have stimulated the development of intertemporal modeling.
After studying this module, you shall be able to examine the needs of intertemporal models, analyze the intertemporal dynamics with the help of optimal control model, understand the multi-period models and dynamic programming for finding intertemporal optimal solution in the economy. Examine basic stochastic intertemporal model. Examine the limitations of the representative agent model of growth. Under static optimization, we aim to find a single value of each of the control variable at which the objective function is optimized. But in a dynamic setting, we need to find the optimal time path of the control as well as state variable during the entire period. Under such models, the control variables in t time period affect the state variables in t plus 1 time period. Let us begin with the discussion of intertemporal dynamic optimization. Main models to solve such problems are optimal control models and the dynamic programming models. These can be applied to deterministic as well as the stochastic models in both discrete as well as continuous time settings. Let us discuss optimal control model. Taking a case of intertemporal utility maximization, we can assume an individual who lives in two time periods and wants to optimize its utility in the entire span of time. His or her utility function can be given by maximization of u ct ct plus 1. with WT as the wage income and ST as savings in time period T, assuming that the returns on savings are R, the budget constraints in two time periods will be CT plus ST equals to WT, or CT equals to WT minus ST. CT plus 1 equals to WT plus 1 plus 1 plus RT plus 1 whole multiplied by ST, or CT plus 1 multiplied by 1 plus RT plus 1 the whole raised to the power minus 1 minus WT plus 1 multiplied by 1 plus RT plus 1 raised to the power minus 1 equals to ST. These two budget constraints can be merged into one intertemporal budget constraint